Hello and good afternoon friends, welcome once again to the CEC-UGC live lecture. Dear friends, continuing from our previous lecture today, we are going to discuss on reaction intermediates, as well as we are going to revise what else we have studied till now in the area of general organic chemistry. And for this we have again with us in our studios Dr. Aprajita Chauhan. Dr. Chauhan is Associate Professor in Department of Chemistry, Aurobindo College, University of Delhi. So, knowing through her what reaction intermediates are, let's continue this lecture further. Hello ma'am, welcome to the ALKYL lecture.
And thank you so much. We'll continue from where we left last time. Last time we were talking about homolytic cleavage, and I told you that because of homolytic cleavage we get free radicals. Now if we talk of a heterolytic cleavage, what type of compounds undergo heterolytic cleavage? Then polar compounds undergo heterolytic cleavage. That is, if there is difference in electronegativity of the carbon and the group attached to it. For example, if I talk of alkyl halides, they will undergo heterolytic cleavage. So the first thing that we have to keep in mind is that there should be difference in electronegativity of the carbon and the group attached to it. Then depending upon that, we can get a carbocation or a carbanion intermediate. If the group which is attached to carbon is more electronegative, then bond breaks in such a manner that that group takes away the bonding pair of electrons, leaving behind a carbon having a positive charge. Such an intermediate in which carbon has a positive charge is known as carbocation or carbonium ion. So what we see here is, because of this heterolytic cleavage, we've got a carbocation. What is a carbocation? Carbocation has 6 electrons in the outermost shell, and the carbon containing the positive charge is sp2 hybridized. It has a vacant p orbital which is perpendicular to it, and it has 6 valency electrons. Since it has 6 valency electrons, it can act as an electrophile or a Lewis acid. Please remember, an electrophile or a Lewis acid is an electron deficient species. So where does it react, or what kind of a species or reagent will come and react with it? It will be a nucleophile. So in most of the cases what we find is that these compounds in which carbocation is formed as an intermediate undergo nucleophilic reactions. Now we can have 3 types. If we talk of alkyl carbocations, then we can have 3 types of carbocations depending on to which carbon has a positive charge. If a carbon which is having a positive charge is attached to 3 other carbons, then it is a tertiary carbon. If the carbon having a positive charge is attached to 2 other carbons, then it is a secondary carbon. And if it is attached to 1 other carbon, then it's a primary carbocation. Now if we have to discuss of the stability of the carbocations, because please remember, more the stability, more the reactivity, more the chance of it converting into product, then tertiary carbocation is most stable, followed by secondary, followed by primary, and the methyl carbocation. We can explain the order of stability of carbocations on the basis of any group, that is electron donating group, that will stabilize the positive charge on this carbocation. And the second thing which we have to take into consideration is the hyperconjugative effect. So more the number of alpha hydrogens, more will be the hyperconjugative effect. For if we look into the first example, it has 9 alpha hydrogens in it. And since it has 9 alpha hydrogens, so many hyperconjugative structures, that this carbocation will be stable because of hyperconjugative structures. The other thing, if we talk of allyl carbocation or a benzyl carbocation, then they are stabilized because of resonance effect. And what we see here is that there is resonance here between the pi bond here and the positive charge. They are in conjugation. So this allyl carbocation is quite stable. Similarly, benzyl carbocation is also stable because it has so many resonating structures. So when we talk of stability of a carbocation and we have to see which is more stable, then we say that a primary between the allyl and a secondary carbocation, allyl carbocation, in spite of being a primary carbocation, it is as stable as any secondary alkyl carbocation. Now if we look into a group which is a methoxy group attached to this group, so in here the lone pair of electrons are interacting with the positive charge, making this carbocation stable, and what we observe here is plus R effect. Similarly, now what we can say is more the number of phenyl groups, more will be the resonating structures. So what we find is that if we have to discuss the stability of different carbocations, that is the aryl and the alkyl, then we say the alkyl carbocation, the tertiary phenyl carbocation, is the most stable carbocation, because there we will have more resonating structures, followed by benzyl, followed by allyl, and then allyl is equivalent to a secondary carbocation, alkyl carbocation, then primary. And please remember, vinyl carbocation is less stable than a secondary carbocation, because here positive charge is on electronegative atom. That is, that carbon which is having the positive charge is more electronegative as compared to a sp3 hybridized carbon. Now if you look into tropylium carbocation, then tropylium carbocation, which is our first example, this is very stable carbocation. This is more stable than a benzyl carbocation, because this is stabilized because of aromatization, that is the sextate, that is it has a delocalized pi electron cloud, because of which it is quite stable, the tropylium ion. So now what we see is, now if we have to look into the benzyl carbocation, then groups which are having electron donating effect, they will stabilize this carbocation through resonance effect. That is, methoxy benzyl carbocation is stable because of resonance effect. Toluyl benzyl is stable because of the hyperconjugative effect. And if we talk of the other and if we have an electron withdrawing group like a nitro group, this will destabilize the carbocation, because it will pull the electrons away from the carbon, thereby making it more electron deficient and it becomes less stable. Now the question arises, where are these carbocations formed as intermediates? See, in all the examples which are coming up, chlorine is more electronegative than Cl, so it will take the electrons when the bond is cleaved. Similarly, what we find in case of primary amines also, nitrogen is more electronegative, it will pull the electrons. Not only substitution reactions, what we observe even in case of addition reactions, if we take in case of alkenes, then there H plus, the electrophile will come and it will result in the formation of carbocations. Then alcohols also undergo nucleophilic substitution or elimination. When we do the reaction with concentrated sulfuric acid, alcohols undergo elimination reactions and we get an alkene. In this case again a carbocation is formed as an intermediate. So if we look at this reaction, what is happening here is a carbocation, that is reacting with a nucleophile, that is OH. So in this reaction, carbocation is acting as an electrophile and OH water is acting here as a nucleophile, and what are we getting here is basically a nucleophilic substitution reactions. So when our carbocations form, if we quickly revise, the carbocations are formed when the group attached to carbon is more electronegative, it will part with the bonding pair of electrons. Now if the story is little different and carbon is more electronegative as compared to the group attached to it, when can this happen? This happens supposing we take a organometallic compound, then in case of organometallic compound there is a bond between a hydrocarbon part and the metal atom. So in that case the alkyl part or the aryl part is more electronegative. Then the second case what we find is, if supposing a alkyl group is attached to an electron withdrawing group like CHO group or NO2 group, then in that cases those will withdraw the electrons towards that self, making that hydrogen, that is the alpha hydrogen, acidic in nature. So carbanions result again as a result of heterolytic cleavage, and since they keep the bonding pair of electrons, the outermost shell has 8 electrons in it. So carbanion will now act either as a nucleophile or it acts as a base. So next thing is, what is the structure of the carbanion? Carbanion, the carbon containing the negative charge, is sp3 hybridized, and the structure around it is pyramidal. Now if we look into the stability of the carbanions, please remember in carbanions, carbon has a negative charge. So anything that will increase the negative charge on this carbon will destabilize it. That means here the order of stability is opposite to that of carbocations. That is, electron donating groups will destabilize a carbanion. So what we see here is a tertiary carbanion is least stable and a primary, that is methyl carbanion, is most stable. Now what we do is we attach electron withdrawing groups to the carbanion, then this carbanion is stable because this will pull the electrons towards itself, thereby increasing the stability of this carbanion. In next case, we have 2 electron withdrawing halogens. They will stabilize the carbanion further. Again, through inductive effect, they are increasing the stability of the carbanion. If we look into the allyl carbanion, then allyl carbanion is stable because of resonance effect. That is, the negative charge is interacting with the pi bond, and we in this next structure we have a negative charge here. So this carbon, this negative charge is delocalized over 2 carbons and it is quite stable. Next what we find is, that is, if an electron withdrawing group, as we've discussed earlier, is attached to a carbon which is having a negative charge, then this carbanion is again stabilized because of minus R effect. So here we have a carbonyl group. So this is a structure of acetone carbanion. This hydrogen has been removed from here, and this group is an electron withdrawing group. So it will pull the electrons towards itself and will stabilize the carbanion. So here what we see are the different resonating structures, and then we have a structure for nitromethane. Here again nitromethane is pulling the electrons towards itself because of the resonance effect, thereby stabilizing the carbanion. Similarly, in another examples also, in acetyl acetone, here we have a negative charge, and this group, it can undergo resonance on 2 sides, and hence this is even more stable as compared to the other carbanions. So now if we have to talk of the stability of the carbanions, more the electron withdrawing groups attached to the carbon which has a negative charge, more is the stability. So what we find is that acetyl, nitromethane, acetone and the ester group, cyano, all these are stable because of the minus R effect which is stabilizing this negative charge. Similarly, benzyl carbonate and carbanion is also stable because of the resonance effect, and the negative charge is delocalized over the entire ring. And if we talk of the triphenyl, then more the phenyl groups, more will be the stability. So triphenyl, then diphenyl, and then phenyl carbanion. Now what we see here in this slide is, that is an electron withdrawing nitro group. That is, if I talk of a nitrotolulyl, this will stabilize it further. This is most stable, followed by a benzyl, and then methoxybenzyl is least stable. This is just reverse of carbocations. If you remember, in carbocations, the order of stability was just the reverse. In that case, methoxy was most stable and nitro was least stable. In this case, it is reverse, that nitrocarbanion is most stable. Now, if we talk of the hybridized atoms, different hybridized orbitals of carbon which are having this negative charge, then acetylide is the most stable carbanion, because the carbon containing the negative charge there is sp hybridized, and we know that sp hybridized orbital is most electronegative between the sp3 and sp2, and it will hold the electrons more firmly, or the negative charge is better accommodated there, and therefore it is more stable. In other words, acetylene, if we talk of the acidity, then we will say acetylene is most acidic. Now, the next question, as we discussed earlier on, when are the carbocations formed? Here again we will talk when are the carbanions formed. So, carbanions are formed when we have a organometallic compound. So, in organometallic compounds, the alkyl group has carbanion like structure, because this structure is covalent bond here is quite polar in nature, and what we find here is a bond between metallic compound and a carbon. Such a compound is organometallic compound. Here lithium will have a partial positive charge and carbon will have a negative charge. Similarly, we talk of methyl lithium, this will again give rise to a carbanion. If we talk of a Grignard reagent, then in Grignard reagent again methyl group has a negative charge and magnesium has a positive charge. If we talk of a base now, see this reaction here, what is happening? OH minus is a base which abstracts a hydrogen from this group, and what we end up here is in a carbanion. And this carbanion is again stable because of the minus R effect here. So, we say if a compound has, if similarly in the second case also, this is an example of ethyl acetate. This group is an electron withdrawing group. So, the bond between this carbon and hydrogen is weak. So, when we treat it with a strong nucleophile, like that is ETO, etho oxide ion, this will abstract a proton from this carbon, resulting in a formation of a carbanion. So, all these reactions, this is where the carbanion is formed. So, now we go on to what are the reactions of the carbanion. So, here what we can say is carbanion is having a negative charge on it. So, that means carbanion can act as a nucleophile also. So, that means when it goes and reacts with any compound, it will go and react where that compound is electron deficient, it will go and react at that carbon. So, when it reacts with a carbon, it is acting as a nucleophile or a So, what we see here in this reaction, the first reaction, the Grignard reagent, from Grignard reagent RT is a minus, and it goes and reacts with the ketone. In ketone, what we know is that the carbonyl carbon has a positive charge on it and oxygen has a slight negative charge on it. So, this R minus will go and attack the carbonyl carbon, which is electron deficient and which is the electrophilic site. And what we have here is a nucleophile is coming or carbanion is reacting here. And then it undergoes, this addition product undergoes hydrolysis to give us an alcohol. This is a very important method for preparation of alcohols, having one carbon more than the parent. So, that means we can convert a ketone into a tertiary alcohol. Similarly, this method again, here is a step up method, that is we are preparing a higher alkyne from a lower alkyne. So, what we find in this case is, that is, what happens here is that this carbon goes and reacts with a acetylidic carbon. When it reacts with an acetylidic carbon, So what we have here is this carbon will go and we will get a higher alkyne. So these are the different reactions in which carb anion will take place, and in all the cases what we are having is one carbon more is formed, that is a substrate is formed with one carbon more than the parent. Please remember, this is carb anion is also formed during aldol condensation. That is, all those aldehydes which have alpha hydrogen in them undergo aldol condensation. This we will be discussing later on. Now the next intermediate that we talk of is carbene. Carbene is a neutral species in which carbon is divalent, and it has 6 electrons in the outermost shell, so it acts as an electrophile. In spite of having 6 electrons, it is acting as an electrophile. It also has a unpaired electron, so it has 2 odd electrons. In spite of that, it is acting as an electrophile because it has 6 electrons. Now when we talk of a carbene, carbene can be of 2 types. That is, it can be a singlet carbene or it can be a triplet carbene. A singlet carbene is when a carbon having the charge is divalent, that is, it is bonded to 2 other atoms, and in it the electron pair, the odd electron pair is paired, so that is also in sp2 hybridized orbital. And this carbene is less stable than a triplet carbene because of the repulsion between the electrons which are in the same orbital. And second, if we find out the multiplicity of singlet carbene is 1, so it is unstable. Now if we talk of a triplet carbene, the second state of carbene that we can have is a triplet carbene. In triplet carbene, the carbon is sp hybridized and the 2 electrons, which are the unpaired electrons because they are having parallel spins, they are present in p orbitals. So here the multiplicity is 3 and this is more stable. So if we talk of stability of carbenes, then a triplet carbene is more stable than a singlet carbene. Now the question comes, where are these carbenes are very, very reactive intermediates and we cannot isolate them. Where and how are they formed? We can have a dichlorocarbene, which is formed when chloroform reacts with potassium butoxide. What we get here is a dichlorocarbene. Secondly, even if we heat diazomethane on heating, that is, we need high temperature photolysis, this will break and we will get nitrogen, and again we will get here a methylene carbene. Similarly, if we talk of this here, a ketene, this will again undergo photolysis and it will give us a dialkyl carbene. What are the reactions of carbenes? Carbenes generally add across the double bond to give us a cyclic structure, or they can even be inserted in carbon and hydrogen and they give us a increased carbon chain, or we go 1 carbon up. So even when they are giving us a cyclic compound, or when we are going, they are being insertion, they undergo insertion reactions, always 1 carbon is more. A very, very important reaction of a dichlorocarbene is a reaction of phenol with chloroform in presence of NaOH. What is this reaction? This is a Reimer-Tiemann reaction in which we get salicylaldehyde. This I will be discussing today later on. This reaction is an example of alpha elimination, one thing, and then this is an example of a reaction in which dichlorocarbene is formed as an intermediate. When I say alpha elimination, what we mean here is that the 2 atoms are being removed from the same carbon. So if we look into the reaction mechanism, what we find here is that OH minus and Na reacts with Cl and it abstracts a Cl from here, we get NaCl, and OH at the same time abstracts a hydrogen from chloroform, resulting in the formation of water molecule, right. So what has happened here is from chloroform, hydrogen and a chlorine has been removed. Hydrogen has been removed as H plus and chlorine has been removed as Cl minus. So what do we get here? We get here a neutral electrophile, that is dichlorocarbene. So this is an example of alpha elimination. So when we look into this, now this dichlorocarbene will go and it acts as an electrophile, and it goes and reacts, or it attacks the sodium phenooxide ion at this position, and we get here this. Now what happens is, since it's a neutral electrophile, so the negative charge of the pi bond is shifted here, and in the next step this H plus, this H will come and form a bond here, and this electrons will go back into the ring which we see in this structure, that is here it has formed bond and here we have a negative charge. Now this negative charge goes back into the ring and we get this structure. This is dichloro structure here, which on hydrolysis will give us salicylaldehyde. This is a very important reaction involving a carbene intermediate. Now the next intermediates that we encounter are nitrines. Nitrines are nitrogen analogues of carbene. In this, nitrogen is monovalent, that is, it is forming one bond, and they can be alkyl nitrine, aryl nitrine, or a acyl nitrine. They are also, just like carbenes, they occur in two states, like in a singlet state in which the electrons are paired, or they can in a triplet state where they are not paired. Next what we have is, where are these carbenes formed? Carbenes are again formed because the nitrogen is monovalent in these. They are formed as a result of photolysis. And what we can get here is a alkyl nitrine, and they are formed as intermediates in Hofmann bromamide reaction. There what we get is, we get a nitrine intermediate. This is a step down reaction, and this we will be concentrating on in our future lectures. So now what we see, that if a compound is polar, then depending on the structure of the molecule, we can either get a carbocation, a carbanion, a carbene, or a nitrine, and if a compound is non-polar, we can even get a free radical. So what happens? Now let us now quickly revisit what we've done till now in general organic chemistry, and then in the next lecture we can take up with different mechanisms one by one and discuss them in detail. So now when we talk of a compound, of an organic compound taking part in a chemical reaction, what is it that we have to first take into consideration? We have to take into consideration, we have to consider, is the molecule polar or non-polar? If the molecule is non-polar, like methane, chlorine, which is an inorganic molecule, or hydrogen, which is again an inorganic molecule, if they are non-polar molecules, they will undergo homolytic fissions to give us free radicals. So first of all, what we are going to concentrate is on the substrate. What kind of a substrate we have? Then second thing is, if a compound is polar, then it will undergo heterolytic cleavage. Now what are the effects which will induce this polarity in the molecule? These can be of four types, as we discussed last time. Three are the permanent ones, which will decide what kind of a reaction will the molecule undergo. First is the inductive effect. Please remember, inductive effect results in the molecule due to difference in electronegativity of the carbon and the group attached to it. Here halogen is more electronegative, so it will pull the electrons towards itself, as a result of which halogen will have a negative charge and carbon will have a positive charge. The next point that you have to keep in mind is, that is the magnitude of the inductive effect decreases as we go away from the electron withdrawing group or the electron donating group, and it is almost negligible at the 4th carbon. The next very important effect is the resonance effect, and its magnitude does not decrease as we go away from the electron withdrawing or the electron donating group, and it results in the molecule when there is interaction between a pi-pi bond, pi and a positive charge, pi and a negative charge, or pi and a lone pair of electrons. And this explains very beautifully some of the unexplained properties of a molecule. When we are not able to explain them on inductive effect, we can explain all those properties on the basis of resonance effect. This we will be discussing quite soon. So what we have is, next effect is the hyperconjugative effect. Now this hyperconjugative effect results in the molecule due to interaction between the pi bonds and the sigma. Now what we have see here is, when this interaction results, there is no bond resonance. This is also known as no bond resonance effect. There is no bond between this carbon and hydrogen, and it results in different resonating structures. Now if we compare these three effects, that is the resonance effect, hyperconjugative effect and the inductive effect, please remember, if in the same molecule these effects are operative simultaneously, that is what I mean here is that in a molecule hyperconjugative and inductive effect is working together, then the magnitude of hyperconjugative effect is more. But if we are comparing hyperconjugative effect and the resonance effect, please remember magnitude of resonance effect is more, because in hyperconjugative one of the structures is having no bond in them. So it is contributing less towards resonance or the hyperconjugative structures, and it is less stable. So that means the most important, the magnitude is of the effect is resonance, followed by hyperconjugative, followed by inductive. So now we will be taking these three effects and discuss the polarity or other properties of a molecule. Now if I talk of an electromeric effect, then electromeric effect is a temporary effect. It results in the molecule when a reagent approaches the molecule. For example, what we see here is that when hydrogen approaches this pi bond, these electrons move towards this carbon, and what I have shown here is that this hydrogen is forming bond with the carbon to which the electrons are moving. So we call this effect as electromeric, and it is plus E effect. That is, the reagent is forming the bond with the same carbon towards which the electrons are moving. So this is plus E effect. Now if we look into the other compound, which is an example of, which is acetaldehyde, which is a carbonyl compound, then here carbon has a slight positive charge and oxygen has a slight, oxygen is more electronegative. So what does this oxygen do? Oxygen pulls the electrons towards itself, as a result of which carbon has a positive charge on it. So when this carbon has a positive charge on it, the nucleophile is coming and forming the bond here. So when nucleophile comes and forms a bond here, these electrons will move towards oxygen. So that means electrons are moving away from the atom to which the nucleophile is making a bond. So this is a minus E effect, that is, electrons are moving away. Now please remember, this effect, the electromeric effect, is a temporary effect. That is, as soon as we will remove the reagent, the molecules will go back to their position, to their normal position, and it involves the movement of pi electrons. Now what is the significance of these effects? Now we will just quickly go through it. First is, we can explain the polarity of the alkyl halides and aryl halides. That is, alkyl halides are more polar as compared to aryl halides, because here we have only minus I effect, whereas in this case we have plus R effect. As a result of plus R effect, this has a partial double bond character. The electronegativity of halogens, the chlorine, is the same, But we know dipole moment is measured by Q into D. So here this distance bond length is less because of which effect? The resonance effect, and the chlorobenzene is less polar as compared to ethyl chloride. Next, we can explain the abnormal bond lengths, that why does benzene have all the bond lengths equal, or we can also explain that why this is butadiene has less bond length. Double bond has partial single bond character and single bond has partial double bond character. Why does it happen? It happens again because of resonance effect, right? Now, not only this, resonance effect or the inductive effect can also explain the basicity or the acidity. Here we say, what is a base? A base is a substance which will give lone pair of electrons, which is rich in lone pair of electrons. So if I look into this structure, ammonia is more basic as compared to hydroxylamine, because in hydroxylamine OH has a effect which is minus I effect, and because of this minus I effect the electron density on nitrogen decreases, and hydroxylamine is less basic as compared to ammonia. If we talk of amines, then ammonia, primary amine, is more basic than ammonia, because in primary amine alkyl group has plus I effect, and because of this plus I effect it increases the electron density on nitrogen. So this is more basic, whereas in hydroxylamine the OH has minus I effect, and because of this minus I effect it will pull the electrons towards itself, and the electron density on nitrogen is less. So that means electron withdrawing groups when attached to basic site atom will decrease the basicity, whereas electron donating groups will increase the basicity. Similarly, what we find is aniline is less basic as compared to primary alkyl amine, because in aniline the lone pair of electrons are involved in resonance, they are not available for bond formation, and it is less basic. At the same time, not only basicity, we can even explain the acidity of acids. So what we find is that is a tertiary alcohol is less acidic as compared to secondary alcohol, which in turn is less acidic as compared to primary alcohol, which in turn again is less acidic as compared to water. Because if you remember in my last lecture I told you that whenever we are comparing the acidity and the basicity, we convert the acid into its conjugate base, and if the base is stable or if the base is weak, then the acid is strong. So in case of a tertiary alcohol, base is strong because it has 3 alkyl groups, and electron donating groups will increase the density on negative oxygen and the base becomes strong. Now if we compare the acidity between phenol and alcohol, then phenol is more acidic, because if you look into the phenooxide ion, then the negative charge on the phenooxide ion is involved in delocalization and it is less available for bond formation. So phenooxide ion is more stable as compared to ethyl oxide ion, hence the phenol has tendency to lose its H plus and to convert into phenooxide. So phenol is more acidic. Now if I look into the effect of substituents on acidity of phenol, then what we find is that electron withdrawing groups like nitro will increase the acidity, whereas a methyl group decreases the acidity. Now if you look into a nitro group here, then nitro group here, because of extended resonance effect here, what we find is it is able to pull the electrons and this base is stable. So nitrophenol is acidic, whereas in this case, because of the plus hyperconjugative effect, the negative charge on oxygen increases and this base becomes strong. So its conjugate acid is weak. Not only this, we can also explain the acidity of the carboxylic acids. if you look into it, then the formic acid is most acidic, followed by benzoic acid and then ethanoic acid. Why? Because in formic acid we have no group which can have plus I or plus R effect, and the carboxylate ion is, the formate ion is very stable. Whereas in case of benzene, phenyl group has a minus I effect, due to which this ion is more stable as compared to acetate ion, because in acetate ion CH3 has a plus I effect, due to which the electron density here is more. So the order of acidity becomes formic acid greater than benzoic acid greater than acetic acid. Now if we look into unsubstituted acids, please remember, as the groups having plus I effect will increase, the acidity will decrease, because these groups will increase the electron charge on the carboxylate ion. This will become stronger, or this will become unstable, and the acid will be weaker. So between the unsubstituted acids, what we have is formic acid followed by acetic acid followed by ethanoic acid. If we talk of butanoic acid or a pentanoic acid, then please take into mind that as the branching will increase, the acidity will decrease, because as the branching will increase, the magnitude of plus I effect will increase and the acidity will decrease. Now if you look into substituted acids, now what I have done here is I have taken different substituted acids, and what I am trying to show is that chlorine has a minus I effect. So it is stabilizing this, whereas in this case methyl has a plus I effect and it is destabilizing it. So chloroacetic acid is a stronger acid than acetic acid. Please remember again, that is, whenever you have to compare the acidic strength, you will always show the structure of the conjugate base, discuss its stability, and then say this is a, if a base is strong, thus say that the conjugate acid is weak. Similarly, more the electronegative group. So what we find here is fluorine is more electronegative as compared to chlorine. So fluorine will have more minus I effect as compared to chloro, as compared to bromo. So fluoroacetic acid is more acidic than chloroacetic acid, which in turn is more acidic than bromoacetic acid. Now if we go on to next point, if we are discussing the strength of the different hybridized orbitals, then please remember, the carbon containing the triple bond is sp hybridized. It has more electronegative atom. It will hold the negative charge more firmly. So that means acetylene is most acidic, followed by ethylene and then ethane. Not only this, what we see is that as the distance increases from the electron withdrawing group from the carboxylic group, the acidity decreases. So the second is 2-chlorobutanoic acid is less acidic than 1-chlorobutanoic acid, because please remember, as we go away, as the electron withdrawing group goes away, then the magnitude of inductive effect, the minus I effect, decreases. So hence this order of acidity. If we look into the next example, then what we find is more the hydrogens we replace with an electron withdrawing group. Here we have one halogen, in the second dichloro we have two chlorines, and in trichloroacetic acid we have 3 chlorines. So trichloroacetic acid is most acidic, because here the magnitude of minus 3 I's will stabilize this ion, the carboxylate acetate ion, very much. So this is most acidic. So what we see is, just by taking into consideration the minus I effect and the plus I effect, the minus R effect and the plus R effect, we can decide the relative acidity or basicity of the compounds. So groups having minus I effect or minus R effect will decrease the basicity and increase the acidity. Now if we talk of the dye substitution in benzene, then what we see here is the group which is attached to the benzene nucleus will decide where will the second group come. So here I have taken another aspect of the importance or the significance of the inductive and the resonance effect. So that means inductive, on the basis of inductive and the resonance effect, we can explain the polarity, we can explain the bond length, we can explain the acidic concept, the basis strength, and then we can also decide which group will decide whether the incoming electrophile will go at the ortho or the para position in case of benzene. So here aniline, in this case, in a case of aniline, nitrogen has lone pair of electrons on it. So therefore, because of plus R effect, it will increase the electron density at the ortho and the para positions. So the incoming group will come at this. So the electrophile will come at ortho and the para position. So that means if I have to convert benzene into, say, ortho formyl aniline, then first I will introduce the amino group and then the formyl group. And if it was vice versa, that is, we had to bring amino group at the meta position, then first we would have done formylation, that is, introduce the aldehydic group. And we know the aldehydic group is meta directing, because here the oxygen is more electronegative, it pulls the electrons towards itself, as a result of which the electron density is less at ortho and para positions. So the incoming group will come at ortho and para. See, this is a very important point. So that means when we will talk of electrophilic substitution reactions, then we have to just talk of 5 or 6 basic reactions, and then those reactions will decide where will the incoming group come. So we just have to know which of the group is ortho and para directing, which group is meta directing, and second, of course, we've got to know the reagents which will bring about formylation or which will bring about nitration, which will introduce the amino group. Just by knowing these groups, these reactions and the basic concepts, the entire aromatic chemistry becomes very, very simple. And we will be discussing this in our later classes. Now, if I go on to next point, if you remember, in our last class, we had discussed on the electrophiles and the nucleophiles. What is a nucleophile? A nucleophile is a reagent which is rich in electrons. So it goes to a reagent to that site which is poor in electrons. So what I have done here is I have taken some beautiful illustrations for you to make this concept clear. Here see, ammonia has lone pair of electrons in the highest filled orbital. So these lone pair of electrons, here it is acting as a nucleophile, and here this borane is acting as an electrophile. It has an empty orbital. These electrons are going from highest fill orbital to the lowest fill orbital, unoccupied orbital. So what we find here is a bond formation takes place. What happens here is a new sigma bond forms, and this is how the electrons flow from the nucleophile to the electrophile, and a bond is formed. So what do we say? That it is a movement of electrons from a nucleophile to an electrophile. So here electrons are moving from nucleophile to an electrophile. And what do we get here? Because of the electrostatic attraction between the nucleophile and the electrophile, and the flow of electrons from this to the H plus, which is acting as an electrophile, we get a bond here, a new sigma bond here, that is bond between HCl. Similarly, in this also we have again shown the flow of electrons from the nucleophile to the electrophile. Now what we see here is that this has a highest filled molecular pi molecular orbital, and this here the electrons, here the pi electrons will flow, whereas in the second example in boron hydride anion, the H minus will go off as a nucleophile, and this will go to an electrophile, which is this here, which has a lithium, which has an unfilled orbital. It flows from here to here. Now if I talk of next, what kind of nucleophiles and electrophiles we can have? This nucleophile, ammonia, acts as a nucleophile through lone pair of electrons. Here bromine acts as a nucleophile through negative charge. Here it is acting as a nucleophile through pi bonds. Here again it is acting as a carbon ion is acting as a nucleophile through sigma electrons. Here again a nucleophile is coming and making a bond with hydrogen OH. We get a water molecule. Water again acts as a nucleophile through lone pair of electrons on oxygen. Here OH is acting as a nucleophile due to negative charge. Here it is acting due to lone pair of electrons. It forms a bond with H plus and it gives us a hydronium ion. So again very beautifully illustrated example of flow of electrons between nucleophile to electrophile. Here again some more examples of electrophiles and nucleophiles, and what we find here is that here in ether oxygen the lone pair of electrons on oxygen are acting as nucleophile and they are going and reacting with boron, which is electron deficient site in trifluoroboron, and we get a reaction here, we get a bond formation, a new sigma bond formation here between oxygen and boron. So flow of electrons again from nucleophile to electrophile. Here also we have shown a flow of electrons, that is hydride, from a boron hydride anion to a carbonyl group forming a new bond. Again all these reactions, all these slides are illustrating flow of electrons from nucleophile to electrophile. Here lone pair of electrons on sulfur are going and reacting with bromine here, which is acting here as an electrophile, and this Br will go off as a negative ion. Now we go on to the electrophiles and the nucleophiles. So please remember, when a reaction takes place, reaction will always take place between a nucleophile and an electrophile. So if my reagent is nucleophilic, it will go and react at the electrophilic site of the substrate and vice versa. So on the basis of what will initiate the reaction, a nucleophile will initiate the reaction or an electrophile will initiate the reaction, we can have nucleophilic reactions, substitution reactions, and if a free radical starts the reaction, we will have a free radical reaction. Now if we look into different types of reactions, the whole of organic chemistry, to make it simple, almost all the reactions can be classified into the following types of reactions, that is substitution reaction, elimination, addition, rearrangement, condensation, isomerization, polymerization, and pericyclic reactions. So what we will do in our next classes, today I will just give you a very brief account. In short, we will be taking all these reactions one by one in detail, discussing their reaction mechanisms. So if I talk of substitution reactions, the substitution reactions can be of three types, that is they can be electrophilic substitution reactions, which are given by benzene and its homologues. They can be free radical substitution reactions, which are given by alkanes, and then they can be nucleophilic substitution reactions. Nucleophilic substitution reactions are given by alkyl halides, alcohols, phenols, ethers. So if I talk of a nucleophilic substitution reaction, what we have to keep in mind is that the atom attached to carbon should be more electronegative. So that means carbon has a positive charge on it. So since carbon has a positive charge on it, then the nucleophile OH minus in case of alkyl halides will go and react with carbon and it will displace or it will replace OH. It will replace, halogen. Now since this is a displacement reaction which is initiated by a nucleophile, we say this is an example of nucleophilic substitution reaction. This again in the later class. Now we go on to, if I talk of a nucleophilic substitution reaction, the nucleophilic substitution reactions are of two types, unimolecular substitution and a bimolecular substitution. Unimolecular substitution, that is in the rate determining step only the substrate takes part, whereas in case of a bimolecular reaction both nucleophile and the substrate will take place. So these conditions, these things have to be taken into consideration when we discuss the mechanism in detail. Here if I look into electrophilic substitution reactions, then in electrophilic substitution reactions, it is the electrophile. See, this case what we have done is we have taken here benzene, and in this benzene I have different electrophiles. Electrophiles, please remember, are what? Are electron deficient reagents, and they will go and react at that part where the electron density is more. So here in case of nitration, the electrophile is NO2 positive. So that is the electrophile. So I have to discuss a lot with you, which I'll be doing in later classes. That will be discussing substitution, nucleophilic substitution, free radical substitution, electrophilic substitution, followed by elimination, addition, and some rearrangement reactions. In the next lecture, what I would like to do with you is, I would like to take up free radical substitution reactions with you in detail, and we'll be starting with alkanes. So that is, if you have any queries, we can get back, or you can just contact us at the email address. Thank you.
With this note, thank you, ma'am. Thank you so very much for explaining us in detail about the reaction intermediates, as well as making the students aware once again with all what you have taught in the previous sessions. I hope that all the students who might have watched us would be benefited from this particular lecture. And I would like to tell you all that if you want to access this particular lecture, definitely you can access us with the help of YouTube. As we always say, that we daily upload our lectures on the YouTube for your convenience, so that it becomes easier for you to watch the programs and study the entire material which you require. Thank you, ma'am. Thank you so very much.